particular of today's class. So, we were looking into the partial differential equations, its definition. There are various types of partial differential equations: homogeneous, non-homogeneous, what is called order of a PDE, what is called a power of PDE. When we call the boundary condition, we are looking into the classification of various boundary conditions like Dirichlet, Neumann, mixed. So, we looked into three boundary types of the boundary conditions. We will look into some more types of the boundary conditions. So, the next boundary condition that we will be looking into is that Cauchy boundary condition. Now, we term that boundary condition to be Cauchy if the if the independent variable and its derivative both are present on the same boundary, then the boundary condition is known as the Cauchy boundary condition. Give you an example in chemical engineering process. For example, if you suppose there is a flow occurring inside a channel and we are looking into the pressure drop profile, then pressure drop profile, the equation will be looking something like this: d square p dx square is equal to some function, maybe a function of delta p. So, in order to solve this equation, we have to have the two boundary conditions, because it is order 2, we have to have two boundary conditions to be specified at the boundary has to be specified. But in this case, whatever is specified is that at inlet point at x is equal to 0, p is known. So, inlet pressure is known, and at x is equal to 0, d delta p dp dx is known, and that is related to a function of inlet flow rate, because that is a measurable quantity. So, since that is a measurable quantity, then dp dx is known. So, therefore, at x is equal to 0, the derivative is also specified, the value of the dependent variable is specified. So, this is an example of Cauchy boundary condition. Next, we talk about something called physical boundary condition. We call that boundary condition as a physical boundary condition, where when the boundary condition is specified, by the physics of the problem. Apparently, the other boundary conditions are not specified. So, in that case, we specified that boundary condition which will be automatically evolving out of the physics of the problem. For example, when you are talking about temperature profile or a velocity profile inside a channel. So, we always define this boundary condition that the middle of the channel, that means at y is equal to 0, del u del x is equal to 0, or del t del u del y equal to 0, or del t del y is equal to 0. This comes from the physics of the problem. It is not that boundary is basically insulated, it is basically it is symmetrical at that particular boundary. So, or we can call at y is equal to 0, t is finite, or velocity is finite. That means, we understand that at the boundary condition boundary at y equal to 0 at the middle of the channel, the temperature must be assuming a finite value, the velocity must be assuming a finite value, but we do not know its value. So, these boundary conditions are known as the physical boundary condition. Similarly, if we talk about the Stokes first problem, what is the Stokes first problem? In this case, suppose there is a stagnant liquid is placed in a domain, we put a stationary plate there. Now, at time t is equal to 0, this plate starts moving in this direction with a velocity u naught. So, therefore, the fluid elements which are coming in contact with this plate, they will be having a velocity u 0 in the x direction because of the no slip boundary condition, and the fluid particle in the y direction. So, fluid particles adjacent to the wall, they will start moving. Similarly, the velocity of the fluid particle will keep on diminishing because of the viscous effect as we go along y. So, beyond a particular point, let us say at y is equal to infinity, the fluid particle does not experience the presence of a velocity, a finite velocity that is present at y is equal to 0. The wall movement will not be recognized or realized by a fluid particle located at y equal to infinity. So, we put the boundary condition that at y is equal to infinity, u is equal to 0. So, since this boundary condition is coming from the physics of the problem, this is also category falls under the category of physical boundary condition. There are various examples of physical boundary conditions where the boundary condition is not apparent, it is not specified by the surroundings, it is not specified by the system. Then we consider that boundary condition, we specify that boundary condition which should be which is in corroboration of the physics of the problem. So, that boundary condition is known as the physical boundary condition. Now, I will just take up one example of a partial differential equation which will be quite common in chemical engineering system. Consider this equation del u del t is equal to del square u del x square plus del square u del y square plus q, and the you require to have one boundary condition, one initial condition or at t, two boundary conditions on x because it is ordered 2 with respect to x, two conditions on y because it is ordered 2 with respect to y. So, typically we have at t is equal to 0, u is equal to let us say u naught, at x is equal to 0, let us say minus k del u del x is equal to q. Let us say it is a heat conduction problem, two dimensional heat conduction, transient heat conduction problem. At x is equal to a, del u del x is equal to 0, at y is equal to 0, u is equal to 0, at y is equal to b minus k del u del y is equal to h u minus u infinity. Okay, let us explain this equation and this set of boundary condition. This equation is a second order two dimensional because it is two dimensional in x and y, two dimensional transient. So, it is time dependent. So, transient heat conduction problem, and there is a source term here, that means there is a continuously there is a source or in the system which will be generating heat energy volumetrically. So, there is a volumetric source term present. So, it is a there is a source present in the system which is continuously developing energy into the system. So, this equation is having order 2 because the highest power is 2. This equation is having a power 1. So, all the terms will be having power 1. This equation is a linear equation because all the terms, there is no terms that is existing which will be having power not equal to 1 and or higher, and there is no term present in this equation which will be basically multiplication of the product of dependent variable and its derivative. So, this is a linear partial differential equation. There is one term present in the equation which does not depend on the dependent variable. So, therefore, this is non-homogeneous partial differential equation. So, these are the characteristic of these equations. It has order of 2, it has a power 1, this is a linear partial differential equation, this is a non-homogeneous partial differential equation. Now, let us look into the boundary conditions. An initial condition at t is equal to 0, u is equal to u 0, that simply means that the initial temperature is fixed, it is given. At x is equal to 0, minus k del u del x is equal to q. This means at x is equal to 0, we have a constant heat flux going into the system, and this constant heat flux is given by q. And at x is equal to a, del u del x is equal to 0, that means the surface located, the boundary located at x is equal to 0 is insulated. So, this is a constant flux condition, and this is insulated boundary condition, and u is equal to 0, that means temperature is 0 there. So, this is the value of the dependent variable is present, and at y is equal to b, the whatever the heat that has come by conduction minus k del u del y is equal to taken away by the air by convection h into u minus u infinity. So, therefore, this boundary condition is containing the dependent variable u and its derivative del u del y, and they are connected by a simple algebraic equation. Now, let us classify the boundary condition. Boundary condition is specified here. So, it is a Dirichlet boundary condition, the Dirichlet boundary condition, and it is non-homogeneous Dirichlet boundary condition, because it is there is a term present which does not contain the dependent variable. Now, let us examine this boundary condition. There is a term contain. So, since the derivative of the dependent variable is present, this is a Neumann boundary condition, but since there is it is not 0, it is q, and that q is it is not a function of u. So, therefore, this equation is a non-homogeneous. So, this is a non-homogeneous Neumann boundary condition. Now, let us look into this equation. X is equal to a, del u del x is equal to 0, derivative of u is specified, dependent variable is specified, and the right hand side is 0. So, this is homogeneous Neumann boundary condition, and y is equal to 0, u is equal to 0. So, value of the dependent variable is specified. So, this is homogeneous, and this is Dirichlet boundary condition. On the other hand, the last boundary condition at y is equal to b, the both the derivative of the dependent variable and the dependent variable are connected by simple algebraic equations. They are appearing in the same boundary condition. So, it is a Robin mixed boundary condition, and there is a term containing which does not contain the dependent variable or its derivative. So, this is non-homogeneous Robin mixed boundary condition. So, in this example we have seen the boundary conditions can be homogeneous, can be non-homogeneous, can be Dirichlet, can be Neumann, can be Robin mixed at the and all these boundary conditions can occur at the same time for the same problem. Okay. Next, we classify the partial differential equation. Okay. So, we consider 3 independent variables. So, and consider the second order equation. Most of the chemical engineering applications you will be landing with the second order equations. So, the general form of the partial differential equation of second order for 3 independent variables are can be written in this form: I is equal to 1 to j 1 to 3, j is equal to 1 to 3, a I j del square u del x I del x j is equal to r x 1 x 2 x 3 del u del x 1 del u del x 2 del u del x 3. So, these coefficients a I j can be function of x's as well. So, we can most of the equations can be cast in this form. Okay. Now, we can have a matrix composing of the coefficients of this of the second order term, then this you can write it as a 1 1, a 1 2, a 1 3, a 2 1, a 2 2, a 2 3, a 3 1, a 3 2, a 3 3. Okay. Now, depending we formulate this matrix and look into the eigenvalues of this matrix. Eigenvalues of coefficient matrix. Now, depending on the sign of the eigenvalue, the partial differential equations are classified. For example, case 1, the first case, if all eigenvalues are of same sign, all may be positive or all may be negative, then this equation, this partial differential equation is called elliptic PDE. Case 2, if some eigenvalues are positive and some are negative, then we call that equation as hyperbolic partial differential equation. Case 3 is that if at least one eigenvalue is 0, then we call this as parabolic partial differential equation. So, that way we can classify the different partial differential equation. So, the form is the idea is we formulate the matrix considering the coefficients of the second order term and evaluate the eigenvalues of the matrix. If the eigenvalues are of same sign, we will be landing up, we will be dealing with the elliptical partial differential equations. If eigenvalues are of mixed sign, that means some of them are positive, some of them are negative, then it is called a hyperbolic partial differential equation. If at least one eigenvalue is 0, then we will be dealing with a parabolic partial differential equation. So, we will take up some of the examples. So, first example is del square u del x square plus del square u del y square plus del square u del z square is equal to 0. So, in this case x 1 is x, x 2 is y and x 3 is z, and we will be having del square u del x 1 square plus del square u del x 2 square plus del square u del x 3 square is equal to 0. Now, if you write it down in this form, I is equal to 1 to 3 a I 1 del square u del x I del x 1. So, just open up the double summation. So, this will be plus a I 2 del square u del x I del x 2 plus a I 3 del square u del x I del x 3, that should be equal to r, and r is equal to 0 in this particular case. So, you just open up this one. So, you will be having a 1 1 del square u del x 1 square plus a 1 2 del square u del x 1 del x 2 plus a 1 3 del square u del x 1 del x 3 plus a 2 1 del square u del x 2 del x 1 plus a 2 2 del square u del x 2 square plus a 2 3 del square u del x 2 del x 3 plus a 3 1 del square u del x 3 del x 1 plus a 3 2 del square u del x 3 del x 2 plus a 3 3 del square u del x 3 square is equal to 0. Now, let us identify the coefficients. If you identify the coefficient, a 1 1 is equal to 1, okay, that is given here. A 1 1 is equal to 1, a 1 2 is equal to 0, a 1 3 is equal to 0, a 2 1 is equal to 0, a 2 2 is equal to 1, a 2 3 is equal to 0, a 3 1 is equal to 0, a 3 2 is equal to 0, and a 3 3 is equal to 1. So, therefore, now if you formulate the coefficient matrix, let us see what is the form of the coefficient matrix. The coefficient matrix is 1 0 0 0 1 0 0 0 1. Now, just look into the eigenvalue of this matrix. You put determinant of a minus lambda I is equal to 0. So, you will be getting lambda is equal to 1 1 1. So, lambda 1 2 3. So, there will be 3 eigenvalues of this particular problem, all are of same size. So, this is an elliptical partial differential equation. Next example we take up and demonstrate how we get a parabolic partial differential equation. Del u del t is equal to del square u del x square plus del square u del y square. We open up the equation as we have done earlier. So, if we really do that and look into the coefficient matrix, the coefficient matrix will look something like this: 1 0 0, because of 1 there will be the coefficient of del square u del x square, it will be 1. Similarly, the coefficient of del square u del y square, it is 1. So, 0 1 0, but the coefficient of del square u del t square is equal to 0. So, therefore, it will be 0 0 and 0. Now, if you look into the eigenvalues of this matrix are 1 1 and 0. Since one of the eigenvalue is 0, then this equation is a parabolic partial differential equation. Okay. So, we go to the next example, that is a hyperbolic one. So, that is example 3, del square u del x square plus del square u del y square is equal to del square u del t square. So, suppose we are talking about this equation. So, you will be having the you can construct the coefficient matrix 1 0 0, because the coefficient with del square u del x square is 1, del square u del y square is also 1 0 1 0, and del square u del t square will be minus 1, because when you bring it to other side. So, 0 0 minus 1. So, one can get the eigenvalues as 1 1 and minus 1. Since the eigenvalues are of mixed signs, then this equation is a hyperbolic partial differential equation. Okay. Now, let us look into next example, example 4. Del square u, just consider this equation del square u del x square plus del square u del y square plus del square u del x del y plus x del square u del x del z minus del square u del z square is equal to a del u del x plus y del u del z plus some function of x, y, z. Now, let us identify x as x 1, y as x 2 and z as x 3, and recast this equation in the form of second order derivative on one side and the other derivative on the other side. So, if you do that, what you will be getting is that del square u del x square x 1 square plus del square u del x 2 square plus del square u del x 1 del x 2 plus x del square u del x 1 del x 3 minus del square u del x 3 square is equal to, let us say, R, and R contains all the first order partial derivative and the non homogeneous term f of x, y and z. So, we put it in this form del square u del x 1 square plus del square u del x 2 square plus half del square u del x 1 del x 2 plus half, just bring it into two parts, break it into two parts, del square u del x 2 del x 1 plus x by 2 del square u del x 1 del x 3 plus x by 2 del square u del x 3 del x 1 minus del square u del x 3 square is equal to R. We utilize the concept del square u del x del y is equal to identical to del square u del y del x. Okay. Now, we write down the coefficient matrix A. So, if you look into the coefficient matrix, it will be 1 half x by 2 half 1 0 and x by 2 0 and minus 1. So, this is a symmetric real value matrix. And of course, it is a real valued. Now, one can identify the eigenvalues of this matrix A. Eigenvalues of this matrix A, and eigenvalues will be depending on x. Definitely, these lambdas will be function of x. So, depending on the values on x, values of x, we classify the partial differential equation. So, in this case, we cannot definitely say about the nature of this PDE, because we do not know the value of x. So, therefore, depending on the value of x, the eigenvalues will be determined, and that will dictate the classification of this partial differential equation. Okay. Next, we go to a shortcut method of classification of PDEs. This is basically a d square u dx square plus 2b I think del square u del x square. So, it will be del square u del x del y plus c del square u del y square is equal to some function of del u del x del u del y, okay, maybe del u del z x y z or any kind of form. Now, if this is the case for a two independent variables, if we have partial differential equation with two independent variable, then all these equations can be and order 2, all these equations can be cast in this particular form. Now, by looking into the values of coefficients a, b and c, we can classify the partial differential equations, and the classification goes like this. If b square minus ac is greater than 0, then we are talking about a hyperbolic partial differential equation. If b square minus ac is equal to 0, then we are talking about a parabolic PDE. If b square minus ac is less than 0, then we are talking about an elliptical PDE, elliptic partial differential equation. Now, that becomes very simple for a two dimensional problem. Then just talk about consider as a problem like del square u del x square plus x del square u del y square is equal to 0. In this case, a is equal to 1, b is equal to 0, but c is equal to x. So, if you compute b square minus ac is equal to minus x, now depending on the value of x, the partial differential equation will be classified. That means, if x is greater than 0, then we talk about then b square minus ac is negative, then we will be landing up with an elliptic partial differential equation. If x is negative, then b square minus ac is positive, and we are talking about a hyperbolic equation, and if x is equal to 0, we are dealing with a parabolic partial differential equation. Consider the equation del square u del x del y is equal to 0. Now, in this case, a is equal to 0, c is equal to 0, but 2b is equal to 1. So, therefore, you can compute b square minus ac, and that turns out to be 1 by 4, and 1 by 4 is of course greater than 0. So, therefore, we are talking about a hyperbolic partial differential equation. So, depending on the for a two dimensional case, we will be we can classify the equations very straightforward manner, but for a three dimensional problem, we have to really compute the eigenvalues of the matrix, of the coefficient matrix where the matrix is formed by the coefficients of the second order partial derivatives, and we evaluate the eigenvalues of that matrix, and depending on the sign of the eigenvalues we can classify the partial differential equations in parabolic, hyperbolic or elliptic. Okay. Next so that goes the classification of the partial differential equations, the different how to evaluate the PDEs, and we defined the different values of boundary conditions. Next we talk about an operator. What is an operator? Ax, consider Ax is equal to y, the matrix A is the matrix, X is a vector, it operates on the matrix A operates on the vector X, and it maps in y, vector y. So, A operates on X to give y, and basically if it is n dimensional, x vector is n dimensional, then y is n dimensional. So, it maps n dimensional vector to m dimensional space. So, this is the operator A. So, similarly, so therefore, we will be having the in case of so this is for the discrete domain for continuous functions. We consider the function u, x and t is differentiable at least twice in x and once in time t, then we consider this function v of x t as del square u del x square minus alpha del u del t. Then we denote operator by L. So, the operator here in this case is del square del x square minus alpha del t, and we write v is equal to L times u. So, in this case, if you just look into the matrix operator and the operator in continuous function, y is equal to a x. So, a is the operator. Similarly, in this case v is equal to L u, where L is the operator. Okay. So, next we talk about a linear operator. What is a linear operator? L is termed as linear operator if L of alpha u plus beta v is equal to alpha L u plus beta L v, then this operator L is called a linear operator, where alpha and beta are scalars. So, therefore, differential is a linear operator. So, d dx of u plus v, let us say alpha u plus beta v is nothing but alpha du dx plus beta dv dx. So, d dx is a linear operator. D square dx square is a linear operator, integration is a linear operator. So, all these are basically linear operators. Now, the idea is when we are having the linear operator, then we can use the principle of superposition. For linear operator, one can use principle of linear superposition. Now, let us look into the principle of linear superposition. We can use the principle of linear superposition for construction of the solution. Consider the ordinary differential. We will take up an example of ordinary differential equation first, then we will explain the principle of linear superposition, then we take up the partial differential equation. Consider d square u dx square is equal to x. This is a non-homogeneous second order ordinary differential equation. Okay. The boundary conditions are u at x is equal to 0 is equal to 5 and u at x is equal to 1 is equal to 10. Both are Dirichlet boundary conditions, but non-homogeneous. So, now there are three sources of non-homogeneities in this particular problem. One non-homogeneity is occurring at the differential equation, another second non-homogeneity is occurring in the first boundary condition, the third non-homogeneity is occurring at the second boundary condition. Then what we can do is that we can break down this problem into three sub problems considering one non-homogeneity at a time, and then we get the solution of each sub problem and add them up, and we will be getting the complete solution. So, that is possible when this. So, because what is the operator in this case? The operator is L u is equal to x. So, what is the operator? Operator L is d square dx square, and we know that d square dx square is a linear operator. Since the operator is a linear operator, we can break down this problem into three sub problems considering one non-homogeneity at a time, and the complete solution can be constructed by getting the by adding them up simply. So, we break down this problem into three sub problems considering one at a time, and the whole solution can be constructed out of it. Let us say u of x, the solution u of x can be constructed by considering y of x plus v of x plus w of x. We break down this problem into three sub parts because there are three sources of non-homogeneity 1, 2 and 3. Next, we construct the governing equation and the boundary condition of each such sub problem. So, now let us write down the governing equation of y. Governing equation of y will be d square y dx square is equal to 0, subject to at x is equal to 0, y is equal to 5, at x is equal to 1, y is equal to 0. So, what we have done here? We have considered the subproblem y and we have considered only one non-homogeneity at a time, forcing the other two non-homogeneities to be 0. So, there were two more non-homogeneities, one is in the governing equation, another is in the boundary condition. We are forcing these two non-homogeneities to be 0 and keeping one non-homogeneity at a time. So, that is the governing equation of the first subproblem with the boundary condition. So, if you like to solve this equation, the solution of this will be dy dx will be c1 and one more integration will give you y is equal to c1 x plus c2. If you put the boundary condition x is equal to 0, so you will be getting y is equal to 5. So, c2 is 5. So, the equation becomes c1 x plus 5, and then we have one more boundary condition, that is x equal to 1, y is equal to 5. So, y equal to 0. So, 0 is equal to c1 plus 5. So, c1 is equal to minus 5. So, we can complete the solution of y, the first subproblem, as 5 minus 5x. Okay. Now, let us look into the second subproblem v. The governing equation of v will be d square v dx square is equal to 0, subject to at x is equal to 0, y is equal to 0, and at x is equal to 1, y is equal to 10. Now, in this subproblem, we are not including the source term in the governing equation, the non-homogeneous term of the governing equation. We are forcing the non-homogeneous term of the governing equation and the non-homogeneous term in the first boundary condition to be 0. We are retaining the non-homogeneous term in the boundary condition at x is equal to 1. So, we are retaining only one non-homogeneity and forcing the other two non-homogeneities to be vanished. So, again in this case the solution will be constituting of c1 x plus c2, and using these two boundary conditions we will be evaluating the c1 and c2 at x is equal to 0, y equal to at x equal to 0, v is equal to 0. This should be v, and at x is equal to 0, v should be equal to 0. So, therefore, c2 equal to 0. So, therefore, v of x is nothing but c1 times x, and what is c1? So, that has to be satisfied by the other boundary condition, that at x is equal to 1, v is equal to 10. So, 10 is equal to c1. So, we can construct the solution of v now. We can construct the solution of v. So, v of x will be nothing but 10x. So, that is the solution of subproblem v. Next, we talk about the subproblem of w. We write down the governing equation of w. It will be d square w dx square is equal to x, subject to at x is equal to 0, w is equal to 0, at x is equal to 1, w is equal to 0. So, therefore, if you look into this subproblem, in this subproblem we are keeping the non-homogeneous term in the governing equation intact, forcing the non-homogeneities in the boundary condition to vanish. Now, you solve this problem, integrate it out once. So, it becomes dw dx is equal to x square by 2 plus some constant c1, then do one more integration. So, this will be w as a function of x will be x cube by 3. So, it will be 6 plus c1 x plus c2. Now, utilizing these two boundary condition, at x equal to 0, w equal to 0. So, 0 is equal to C2. So, therefore, w x becomes x cube by 6 plus C 1 x, and at x is equal to 1, w is equal to 0. So, 0 is equal to 1 upon 6 plus C 1. So, C 1 is equal to minus 1 upon 6. So, w x becomes x cube by 6 minus x by 6. Now, now we can use the principle of linear superposition and add all this solution up, and we will be getting the complete solution. So, u of x is equal to y of x plus v of x plus w of x. We have already found out that the expressions of y and x, y and v, y is 5 minus 5 x plus v is 10 x, w plus x cube by 6 minus x by 6. So, this becomes x cube by 6 plus 5 x minus x by 6 plus 5. So, x cube by 6 plus 30 minus 1. So, it will be 29 by 6 times x plus 5. Now, if you look into the original problem, so that is the complete solution u x. So, by using principle of linear superposition, one can construct the complete solution. Now, if you look into the original problem, the original problem was d square u dx square is equal to x square subject to u at x is equal to 0 is equal to 5 and u at x is equal to 1 is equal to 10. So, just do it by one integration. So, one integration will give you du dx is equal to x cube by 3 plus some constant c 1. One more integration will give you x to the power 4 by 12 plus c 1 x plus c 2. The original problem was d square dx square is equal to x. So, it will be x square by 2, then it will be x cube by 6 plus c 1 plus c 1. So, it will be x cube by 6 plus c 1 x plus c 2. So, now we put the boundary condition at x equal to 0, u is equal to 5. So, c 2 equal to 5, you put x is equal to 0 and u equal to 5. So, you will be getting c 2 equal to 5. So, therefore, u of x is nothing but x cube by 6 plus c 1 x plus 5. Next, you just put x is equal to 1, u is equal to 10. So, 10 will be 1 over 6 plus c 1 plus 5. So, if you evaluate, c 1 turns out to be 10 minus 5 is 5, 5 minus 1 upon 6, it will be 29 upon 6. So, the complete solution of this problem becomes u as a function of x cube by 6 plus 29 by 6 into x plus 5. So, that matches with our solution using the principle of linear superposition. So, this is quite straightforward and understandable for an ordinary differential equation. We demonstrate this particular method for ordinary differential equation. Now, nobody will solve this problem by breaking into 3 parts for ordinary differential equation, rather they will be utilizing this route to solve this problem. But this problem in ordinary differential equations, we have given a demonstration to illustrate the method of application of principle of linear superposition. So, this method will be quite useful for solution of partial differential equations, and then this becomes very handy, becomes very useful method, and in the next class we will be outlining how this method of principle of linear superposition will be applied for the solution of partial differential equation. Thank you.